Okay, today we are going to talk about nuclear chemistry and radioactivity, which is an integral part of nuclear chemistry and learning about the atom. On this first slide, you just have some real-world examples of where we use nuclear chemistry in today's society. We can use it as a power source. It's used to treat our food to make it safer, with the strawberries down here. So there's a lot of applications in healthcare where we use it both in diagnostic tests as well as in treatment of different diseases. And then in some of our everyday items like smoke detectors, we use different radioactive materials as well, obviously in safe doses so that they don't cause harm. Okay, a few things we got to do is review some concepts that are really crucial for nuclear chemistry. The first one being that we know that the nucleus will contain protons and neutrons, okay, which again, we've known that for a while. Atomic number is the number of protons. That's what determines something as a certain atom. For example, all carbon atoms have 6 protons. That's what makes something carbon. The mass number is going to be the number of protons plus the number of neutrons. Isotopes only differ in numbers of neutrons only for the same atom. And a nuclide is a new term that we've not talked about that's just a specific type of atom, or a member of group of isotopes, if you will, which is identified by the number of protons and neutrons. For example, carbon-12 versus carbon-14. They both have 6 protons in them. Carbon-12 would have 6 neutrons. Carbon-14 would have 8 neutrons. They would both be examples of nuclides for carbon. Now, for designated isotopes, there's 2 forms, which we've already covered. The hyphen notation has the element or symbol, a hyphen, hence the name, and then the mass number, whereas the nuclear symbol is the mass number on top, the atomic number on the bottom, and then the chemical symbol. Again, all things we should be familiar with at this point. Now, we have to differentiate between a few pairs of terms before we get into them. The first 2 terms are chemical reactions versus nuclear reactions. Big difference here, chemical reactions typically do not involve changes to the nuclei. Okay, there may be electrons that are lost, gained, or shared, but you typically do not have any changes to the nuclei. And we've already seen examples of chemical reactions where a new chemical is formed on both sides, on the other side of the reaction. Nuclear reactions, in contrast, then do involve changes to the nuclei of atoms. Okay, so that's going to be a big one there. Electrons may still be lost, gained, or shared, but there has to be changes to the number of protons or neutrons in the nucleus, hence the name nuclear reaction. Now, a couple of other big terms that are in pairs here. You have nuclear fission, which occurs when a heavy nucleus splits into more stable nuclei. I always remember because there's an ion splits and 2 ions in fission, as opposed to nuclear fusion, where you have lower mass nuclei combining to form heavier. One of the other commonalities here is that for both of these, it's a more stable atom configuration. We're going to find that there are some patterns of stability for ratios, which are kind of beyond the scope of this course, but they are there. And but for fission, it's going to split. Fusion, it's going to come together. Okay, now a couple of terms that are often confused are radioactive decay, which is the spontaneous disintegration of a nucleus into slightly lighter nuclei, or a slightly lighter nucleus accompanied by the emission of particles, electromagnetic radiation, or both. So radioactive decay is the process. It's the actual disintegration and the spontaneity of it, whereas nuclear radiation is going to be the actual particles or the radiation they're emitted. So the decay is the process, the nuclear radiation is what is emitted, or what things are decayed into. So that's the easiest way to keep those 2 straight. Excuse me. Okay, now we're going to go through several different types of, oops, a little too far there, radioactive decay. The first one being alpha particle production. Okay, an alpha particle is 2 protons and 2 neutrons that are bound together and that are emitted from the nucleus during radioactive decay. An alpha particle is going to look a lot like a helium atom, because it's actually a helium nucleus, where you're going to have helium, 4 for the atomic number, the mass number, 2 for the atomic number. Okay. Now, the way that you often see these written is as in an equation. So, for example, if I start with uranium-238, okay, and the question might read, write a balanced equation for the alpha particle production of the decay of uranium-238. So what we would get on the other side would be the helium atom that was the example of the nuclear radiation that was given off, and then we have to figure out what's left. And actually, to do that, it's a pretty simple process. We take 238, we subtract the 4 that was given off, we get 234. We then take the 92 that we started with, we subtract the 2 protons that were given off, and we're given 90. And then all we have to do is go to the periodic table, find the element that has 90 for its atomic number, and it's going to be thorium, which is a symbol of TH. Okay? And that's it. So that's alpha particle production. As always, if you have any questions, jot them down, email me, we'll get them answered. Okay, the next one that we've got is beta particle production. Alpha particle was discovered first, beta particle was discovered second. A beta particle is where an electron is emitted from the nucleus. Alright, now that may sound odd because hopefully we recognize that electrons usually aren't in the nucleus. But essentially what happens here is we take a neutron, we rip off its negative charge, and we turn it into a proton. Okay? So how do we write that? Well, our symbol for the electron is going to be an E, 0 for the mass number, because remember when we looked at the mass of electrons, it's 1/1000th of an AMU, so it's pretty small, and we put -1 there to represent the fact that it's negatively charged. Now, to give you an example of an equation, if we take that same thorium-234 and we split it by beta particle production, the first thing that's going to happen is we're going to give off an electron. Okay, that's what beta particle production means. So we've got to represent that electron being emitted. Then we have to do some math. Now, the top number, that one makes sense. 234 minus 0 is going to be 234. Okay, not so bad. Well, it'd be really nice if it was 90 minus 1 to find the bottom number. Not quite so easy. What's going to happen is we take that 90, remember we're taking one of these neutrons, we're ripping off the negative charge, and we're turning it into a proton. Not sure where that came from. Alright, so instead of subtracting 1, we have to add 1. So we're going to get 90 plus 1 to give us 91. Again, we go to the periodic table, we find out that the symbol for the element that has 91 protons is Pa. Okay, I know it's a little backwards, but this is the only one where the math kind of really doesn't make sense. Alright, now gamma ray production. Gamma ray production is an example, and we hear of gamma rays in a lot of times in healthcare. Sometimes they're used for taking x-rays. They're very high energy electromagnetic radiation, and we'll cover this more in detail later. So a gamma ray is a very high collection of high energy photons. Now we haven't really talked about photons, we're not really going to spend a lot of time on them, but we don't really have a tangible mass to them. So you're going to see that the numbers make it easy. Gamma rays typically happens in accordance with other types of decay, and essentially it helps the nucleus release extra energy and go to a lower energy state. So what does that look like? Well, gamma rays we write like this. Zeros, because no masses, no charges, and this kind of funky lowercase gamma. Okay, that's a bad gamma, but you get the point. If you draw a Y, it'll be okay. Now, the way that you'll have to write these is if it happens in accordance with other reactions. So if we go back to our alpha particle production for uranium-238, where remember the alpha particle again is a helium nucleus, we decayed it into thorium-234, okay, and if it said uranium-238 undergoes alpha particle production and gamma ray production, then what you would have to recognize is that, let's see if I can do a better gamma. That's a little better. Okay, you had to also include the gamma ray, but it's going to tell you that. It's not something that you just have to spontaneously remember. Okay? Now, the other thing with gamma rays is that, like we said, gamma ray, the energy is emitted as neutrons are divided and rearranged. So really, it's just allowing the atom to rearrange itself and reorganize itself, okay? And it can be stopped by about 10 plus, this should say millimeters, of lead, but it usually can pass through the body, and that's the reason that when you go to the dentist they put the lead apron on you, is so that the x-rays only make it to your mouth where it is beneficial to take the picture, as opposed to passing through your body and doing some other damage. So those are gamma rays. Okay, 2 more. The next one that we're going to have is positron production. Just sounds kind of cool, positron. Okay, positron is a positive particle with the same mass, well, my version of cool, but positron is a positive particle with the same mass of an electron. Okay, so when we write positron, we're going to have 0, we're going to have electron, only we're going to have 1. Now, sometimes to differentiate, I'll write +1 just to remind you, but you don't have to put it that way. It's also called an antiparticle of an electron. Now, antimatter is kind of this really awesome branch of science. If you've read Angels and Demons, or if you're into the particle collider research that's going on, it's really fascinating stuff, but we don't have time to get into the science of it. So, in other words, it's just the opposite of an electron. And its net effect is that this time it takes a proton and turns it into a neutron. Okay, so what does that look like? Well, if I take sodium 22, okay, and it undergoes positron production. Now, all of these, every single one of these particles is one of the products, okay? It's on the right-hand side of the reaction. Well, if I generate a positron, 0, +1, and the electron, all right, remember what's going to happen here, and it kind of goes hand in hand. All right, I wasn't telling the truth. Math doesn't totally make sense here either, but it's the opposite of a beta particle production. So we're going to take one of these protons here, we're going to turn it into a neutron by essentially ripping off a particle, a positive particle. So what we end up with is the 22 is going to stay the same up here, but we take one of these protons and we turn it into a neutron. So just like beta particle production, the math was opposite, the math is opposite here too, where we have to take the 11, get rid of one of those protons, turn it into a neutron, and we're left with 10. And if we go to the periodic table, we find the 10th element, we're going to see that that is neon, which is one of the noble gases way over on the right. Okay? Alright, now last but not least is electron capture. This definition, I think at least makes sense. For electron capture, it's where one of the inner electrons in an atom is captured by the nucleus. I always think of that Hungry Hippo game. You may be too young to have played this, but there were these hippos that reached out and grabbed the marbles and pulled them in. So that's what I always think of as electron capture, but that's just my brain. Alright, now electron capture is one of those situations where gamma rays typically are always produced on these. So we will get gamma rays. I believe your notes actually say that. But, so if we had an example of this one, if we had mercury 201, okay, and we get the electron capture. Now this is the only type of decay where we're actually going to have the particle as a reactant. So it's captured, it's brought in, meaning it's on the left-hand side of that arrow. Now what we end up with here, the math on top is going to stay the same, so 201, and the math is actually going to make sense here for the electrons. We take 80, we subtract 1, we get 79, and it turns it into gold. This was actually one of those mystical alchemist reactions that they were all aiming for in the medieval Middle Ages stuff, but anyway, totally separate issue there. Okay, and we're going to have the gamma ray production, so we're also going to have some gamma rays produced. Okay, now this last statement here is really just a explanation, so to speak, is that when we see this radioactivity happen, it actually really happens in several steps and several types of decay. Very rarely is it a one-step boom process, and we'll take a look at some of these to show you examples of those.